Uh, I'll wait for 2-3 more minutes for everyone to join. Yeah, so we have a very less amount of participants today. Okay. Okay, so I welcome to all who are present today. Greetings of the day, and greetings of the day to those who will be watching this lecture on YouTube. Anyways, so I welcome you all to week 4 doubt clearing session or problem solving session for the course Smart Grid Basics to Advanced Technology, uh, being taken by Professor NP Padhy and Professor Premlata Jena. I am Swastik Sharma and I am a TA for this course. I'm doing my PhD from IITK. Let me share my screen. Yeah, so apologies in the beginning only if I cough a lot in between. My health is not very good. So yeah, so last week we discussed, we started our discussion towards uh, the so we started with what are DERs, what are various forms of DERs, and then we shifted our focus to the what you say. I forgot what was taught last time. Yeah. So can anyone remind me what was there last time? Yeah, we talked about energy storage systems, right? Yeah. So today we will shift our focus and we'll talk about how we monitor these large amount of these resources which are present at different parts of power systems, and we'll talk about uh, what is wide area monitoring system, how it is done, and what are the different terminologies associated with it. So let's start. So first of all, what is wide area monitoring system? So why do we need to monitor our system? So we have a large we have a large amount of loads dispersed across different um, uh, what you say uh, corners of the power systems, right? So we need to measure and prevent sorry, we need to monitor and prevent their loss, because if let's say due to generation blackout, there is a huge amount of costs associated with it. So there's a term used in economics, mostly it's called value of lost load. It's like it's given in dollars per megawatt hour. It tells you the value which is associated with the lost load due to blackouts, brownouts, etc. So this is used to calculate uh, to to tell about why security or why monitoring is required for the power system. So this value of lost load is in huge numbers. It's I guess it's between $2,000 to $3,000 per megawatt hour, right? So it's a very high value. So to be able to monitor and prevent their loss, we usually need to monitor the system. So for that, wide area monitoring systems came. Now we used to have monitoring systems in place, right? This was SCADA. So what happened was SCADA, even though it was used, but technologies grow. More and more different kinds of devices are integrated to the systems at different points of times, right? With growing technologies, you need to continuously evolve your monitoring strategies as well, right? SCADA at that point of time was doing its job well suited for the purpose. Now, when different DIAs are integrating into the power systems, we need to start implementing, or we need to start thinking of how to evolve these monitoring systems as well. So that's where the VAMs or wide area monitoring system came into picture. So so what exactly is it? It's similarly to the SCADA. SCADA had RTUs, remote terminal units. Here we use PMUs to measure phasors related to voltage and current. And uh, can anyone tell me what are phasors? So I've explained it before. I guess you must be comfortable with the terminology. What are phasors?
Sir, you told us that the phasors are the rotating vectors.
Yeah. So phasors are rotating vectors. So they tell us both they so since they are vectors, they tell us the magnitude as well as the phase angle between different quantities, right? So the voltage and currents are usually measured in terms of their phasor. We usually estimate them as phasors, right? So that's where phasor measurement units come into play. They are used to measure phasors of different quantities, and these are then used to calculate various different. So when you have voltage and its angle, let's say VA, VP, and VC, you can find the associated if you know the plus you know the network configuration, that is, let's say yij. So if you have these things with you, network configuration, so if I say that if you have these things, will you be able to calculate power, this reactive power, etc., etc.? Is it true? Can I say that given these quantities with you, can you calculate the rest of the parameters? So the answer is yes. So load flow, you have only you have two state variables. It's the voltage angle and the this magnitude, right? So you need to have these two quantities to be able to calculate the power injection, power flow, etc. For the whole line. We'll talk about it more. So yeah. So since in real time we want to provide the system with real time knowledge, so what we do, SCADA, even though it was telling us about the various different parameters. So, can anyone tell me? I remember telling you in lecture one what are the quantities SCADA sends to the control center. So, does anyone have any idea? You can open your lecture one notes also to check. So, let me tell you. So, it tells you about the magnitude of the voltage, the power injection, and the flow of power on lines, right? So it was used to calculate these five different parameters. Here in BAMS, we only have phasor quantities, that is voltage and its angle and current and its angle. So using these quantities, we can calculate through load flow all the other aspects of it. So let's say you know the network. So if you know the network, the formula is something like this, right? So this is by using this, you can calculate the complex apparent power associated with the flow of uh, with these variables, right? So VAMS uses this basic technique that you only need two state variables to be able to calculate everything related to the network that you want to do. So one more thing it offers is it offers the resolution of the data. So SCADA collects data every 1 or 2 seconds, while a VAMS could collect timestamp data 20 to 60 times per second. So the resolution of data is more. So you can gather more data for in a similar amount of time, it's 20 or 30 times more than what it was doing in SCADA before, right? And since it's timestamped and it's sequenced, what you can do is you can check at what time fault began, how did fault proceed, what happened, what caused the fault. Everything could be known because VAMS uses PMUs, which use timestamps to figure out the data, to send the phasor data to the different load centers, right? So this is how a VAM structure is. So you have different so you have a network. It's connected to a generating station using a transformer where also you have a PMU. So you can have disperse these PMUs at different places. And it's not like you can put a PMU at any place you want. So PMUs are a costly equipment. For that also you can solve an optimization problem for figuring out the optimal placement of these PMUs. So this is a completely different avenue which was not discussed, but still I'll discuss afterwards. So you can have different PMUs at different dispersed at different places in the whole network, marked by these red dots. And you can have local PDCs. The PDCs are phasor data concentrators. So PMUs are in contact with their local PDCs, where all of these phasor data is sent, and the PDCs then evaluate this data, store this data, and send it to the control center. For distribution systems, you have another thing. It's called micro PMU. So why micro PMU? It's because first they are a bit smaller in size. Second, their time resolution is quite high. So because of which, what happens is, since distribution, you have so many different kinds of disturbances happening, right? You switch on a load, you switch off a load. It's a disturbance, right? To monitor those, you need a larger resolution of data, right? So there, it's linked with micro PMUs, and all of this is connected with the super PDC. Super PDC is at the top of the hierarchy, where the local PDC send it to the PDCs, which then using the Ethernet or wide area network send it to the control center. So this is how a WAM structure usually looks like. So I'll come to EMS later. So since I mentioned that they use PMUs, right? So what exactly is PMUs? I already told in my first lecture. So PMUs are phasor measurement units. So they calculate voltage phasors and current phasors. This then they so using which we can get the injection flow, etc. at all buses. So these PMUs are used for wide area situational awareness. That is that sitting at a control center, you can monitor the whole network of the entire country. In India, at least, so we have the NLDC is the phasor data concentrator, which is our control center as well. So sitting at Delhi, you can monitor all the PMUs dispersed across different you RLDCs or different regions. So it provides a wide area situational awareness for system operators, which results in improved visibility into dynamic grid conditions. Second, we can determine stress points of the electric power system. So let's say since we have PMUs at different, we can calculate the buses at which voltage is sagging, or at places where frequency is dipping. So that's the points after knowing those points, you can invest in resources so that, let's say you can invest in reactive power dispatch for sagging issue, and then you can use real power dispatch for frequency issues, right? Third, they can provide instantaneous measurements, and this results in early warning detection. So let's say because you are sampling quickly in let's say milliseconds. So what's happening is that you can provide this information quickly to the system operator as well. So the system operator can then take corrective actions using these instantaneous measurements provided. Whereas SCADA missed this completely because it was taking samples every 1 to 2 seconds. Now, built-in system-wide PMU analysis for future implementation. Okay, so you have big data analytics as well. So what is big data analytics? So you have a large chunk of data, right? So you can use this data by you can check how this data is behaving to be able to use artificial intelligence as such to do non-intrusive load monitoring, or other various applications if you can find. So you can use it to, so since you have access to data, right, so why not use it for the betterment of the power system? That's where this PMU comes into play. So the major application is transmission monitoring, distribution system monitoring, and DER monitoring. So since you have DERs, right? So DERs are what, they are in feeding power back to the grid from being at the distribution side. Now you're feeding back power back to the main grid. So what's happening? These can also cause faults. These can also cause disturbances due to reverse power flows. And to be able to monitor that perfectly, you can use these PMUs. So you can see in this figure, you can see there are disturbances occurring for a very less amount of time, right? PMUs are able to catch that because they are sampling quickly and efficiently. But SCADA, since it's not sampling it quickly, it's not able to correctly tell how the disturbances are occurring at a per unit basis, right? So it's the sampling that's causing you how to that's telling you how the transients are occurring in the system. So that's where you are interested. Let's say, for example, this is a huge transient. I mean, not huge for the system, but it's a transient, right? So SCADA was not able to tell this how big this transient was, but PMUs are. So it's the resolution of the PMU that helps in doing this thing. So yeah, this was in the PPT itself. So it's one sample every 2 to 4 seconds for SCADA, whereas it's 10 to 60 samples per second for micro PMU, giving it sorry, for PMU, giving it a dynamic or transient observability. It could measure only the magnitude. So you were leaving out the information that was there associated with phase angle. So for rotor angle stability, etc., you were not able to do that because you are only getting the magnitude out of it. But here you are getting both the magnitude as well as phase angles. SCADA was not synchronized perfectly with time, while PMUs are. You use a GPS where it's connected to a UTC time, which is coordinated universal time, to issue signals based on this UTC time frame. You had a large amount of analog and digital input output pins, and whereas here they are less, and you want only for the phasor quantities. The focus of SCADA was for local monitoring and control. Now the focus of PMUs is wide area monitoring and control. That's what you want. So at first, what we were doing, instead of having people at remote locations, we wanted SCADA to help a small control center to be able to issue commands remotely, right? You don't require to go to the place to be able to issue trip commands or or other commands. But here, now what you're doing, you're increasing the bandwidth of the system operator. So now, instead of having local operators, you can have only a single operator at a higher level, which can monitor the entire network of a country, let's say. So how do they do it? So PMUs are located at various substations, which are then connected to various data concentrators. So the role of data concentrators is to gather data. First of all, they gather data from all the PMUs, and then they reject bad data. So since the time frame is less, you can have multiple amount of noises associated with it as well, right? So you don't want that noise to act as a transient for the system operator to take action. So what it does is it rejects bad data as well. Third, it aligns the data with timestamps. And fourth is it creates a record of all the things happening in the all the information related to the, it creates a record of all the things happening in the power system. So and this is how the communication between PDC and PMU occurs. This is self-explanatory. So as I told you earlier as well, so it's not like you can place PMUs at every part of the transmission side or distribution side. You can, it's a costly affair, and to be able to do that, you need to solve an optimization problem where you find the optimal PMU placement. So for that, if interested, people who are interested, they can check this this reference. It's a Saika Chakrabarti sir's reference. He's a professor at IIT Kanpur, and it tells you how the optimal location of PMUs could be done for the IEEE 30 bus system as well as the New England 39 bus test system. So yeah, so just a second, am I missing something? Yeah. So let's talk about their application. So since we are doing wide area monitoring, right? If it's not for, so we need to do it. It's a costly affair. So their application should be properly be their application should be talked about appropriately. So for generator, you want the generation status operating management and transient angle stability. So that's what was missing before because SCADA was only giving you magnitude. You were not able to tell how the rotor angle was behaving at that place. For transmission, you need state estimation. What is state estimation? So you have two state variables. I told in the beginning of lecture itself. Can anyone repeat what are the two state variables? So state variables are those variables which can be used to calculate which can be used to derive other parameters associated with the power system. So what is state estimation? Anyone? Sorry, what are the two state variables? Anyone? There are two state variables. I told you, right?
Sir, voltage with the angle and network parameters configuration.
No. Network configuration is not a state variable, right? Network configuration won't change in real time. It's just the voltage uh, for load flow, for optimal power flow, for forecasting, and for economical dispatch. So you want to dispatch resources economically, right? You solve an optimization problem for that as well. So people who are interested, you can check. So for that as well, you require VAMs in order to get the real-time info of the system. Until and unless you know how the system is behaving in real time, you won't be able to do the economical dispatch. And for that, VAMs comes into play. Third is at the distribution side. For distribution side, for substation automation, since you have PMUs, you can use it to issue commands automatically. So it can be used for service restoration. It can be used for bus voltage control, where it can automatically use the devices available for reactive power dispatch, such as capacitor banks, to control the bus voltage if it's sagging, and then a line drop compensation. So if there's a large line drop, if it means that I square R losses are more, it can be used for that as well. And then for automatic reclosing. So what is reclosing? So whenever a fault occurs, the the reclosers sectionalize the area. That means they withdraw power from that area for a small period of time, and when the fault is cleared, you want that area to be again reconnected with the whole system. So for that, you can automatically issue the command through VAMs. Then you have feeder optimization, and then you can use it for consumer side automation as well. So yeah. So for smart grid, what are the so this was something that I wanted to discuss. So to monitor a smart grid, what are the various things that are first of all affecting the way they monitor it is the DER. So earlier, what was happening, the the whole generation, transmission, and distribution was a what you say one-sided power flow used to took place. So generating side had the generators which sent power down the transmission lines to the distribution side. But now a reverse power flow phenomena is being seen because distributions are sorry, shouldn't say till generation, but yeah, because distribution systems also are taking active are becoming more active because of wide DRs connected with it. So for that, you need to be able to measure the oscillations that are occurring in the voltage and let's say the voltage and phase angle, or sorry, frequency. So, and then you need to measure the stability as well. So, in order to ensure that efficient uh, flow of power is being issued from the whole smart grid, you need to make sure that it's stable at first. So, how does the PMU work? So, this I think I discussed in the first class itself, but again I'll discuss. So, you have a GPS receiver. It's connected with a GPS clock. So, this GPS clock is nothing but a cosine reference which is connected with UTC, which is coordinated universal time. So, what is this GPS clock? So, it's linked with satellites. It's linked with 24 satellites, I guess, in 6 orbits. And so, at a height of some roughly 10,000 miles, right? So there are 24 satellites in 6 orbits, and they are connected with, they are at a height of 10,000 miles. This is where the GPS clock is getting the time signal of the whole, how the solar clock is, so how is time measured? It's nothing but how the yeah, solar light is falling on the Earth's surface, right? And that's is being monitored using these 24 satellites. So these cover approximately 42% of the globe at any point of time, right? Each covers 42% of globe, right? So this GPS clock, which is a cosine reference, is used to phase lock with the inputs that it's receiving from the analog input. So what are the inputs? It's the voltage and current from PT and CT, so potential transformer and current transformer, which is then fitted with an anti-alias filter. I'll discuss about anti-aliasing, which is then converted from analog to digital, and which is logged with the GPS clock, which is the cosine reference, combined with the UTC, which is then sent to a microprocessor which calculates the phasors associated with the voltage and current, and it then sends it back to the control centers or the phasor data concentrators using this modem. I am repeating what I told in the first class. So, in order to do this, we need to sample first. So these analog inputs must sample the current or voltage, uh, what you have said, signals appropriately. So these are the two uh, what I say is how sampling affects the nature of the signal. This is what I want to confirm. What I want to uh, tell you from these two images, right? So the first one, you are sampling at a rate of, I guess, 1 millisecond, and the other you are sampling it at a rate of 25 milliseconds. So if you see, when you're sampling at 1 millisecond time, you have a large number of samples. These are 22 samples, 20 samples, sorry. And here there are only, so it's 25, which is 1 upon 25. So how much is it? 400, right? It was 0.0025. So oh, it's 2.5. Yeah. So this is 400 hertz. So here you are sampling at 1 kilohertz. Here you are sampling at 400 hertz. So the number of samples here will be 8, and the number of samples here are 20. So you can see when you have these many samples, the shape of the input, the current signal is distorted in this diagram, while here it's completely reproducible, right, with the samples that are being taken at 1 millisecond interval. So sampling affects the phenomena by which we so these this sampling affects how the signals look in real time. And what is aliasing? Aliasing is nothing but when there is a high frequency component, when it is sampled at a lower rate, it starts looking as a fundamental or a lower frequency component. So in this case, let's say that we have a fifth harmonic. A fifth harmonic is then 5 into 50, which is 250 hertz. And if we sample it using 0.02, it's how much is this? Yeah, it's 2.5 milliseconds, right? So when you're sampling it with this rate, what is happening? It starts looking as if it's a fundamental frequency, this green curve, if you see. So in order to uh, be able to properly lose this aliasing component, what you need is the anti-alias filter. This can be basically what you do is you can use a low pass filter coupled with your analog inputs to be able to remove this low frequency signal from your fundamental component. So sorry, the high frequency component from the fundamental component. So when you do that, you won't get the aliasing phenomena for this harmonic. So yeah, so that's how anti-aliasing is important. Uh, yeah. So hmm. So this is all about how the PMUs work, and at distribution side, so what you need is you have the whole distribution system coupled with various PMUs. So this helps in doing what? You can do network reconfiguration in real time. You can sectionalize areas. That is, you can open switches or close switches, and you can do topology expansion as well, whereas you can connect different feeders with the main feeder, and only after doing optimal PMU placement. So this is how the distribution system state estimation works, where you want to find the state of the all the different buses, which are the voltage angle, voltage magnitude, and phase angle. For this, you use a state estimation algorithm. These are complex algorithms which are uh, for sake it's weighted least square. One is called weighted least square. So we'll discuss about least square estimation in the coming slides. Yeah. This is how the PMU operation is done. You get voltage and current signals, and then what you do is, yeah, one more thing I forgot telling you. In order to lose aliasing, I told you, right, you have to sample at a higher frequency. This sampling is judged by Nyquist criterion, which is, sorry, which says that the sampling frequency, yeah, your sampling frequency must be at least twice the maximum frequency component associated with your signal, right? Uh, so if you do this, you it the you can assure that your signal won't have aliasing, right? So yeah, uh, yeah, so yeah, so you have so you what do you do? You get the voltage signals. These are in red. The red pen, the voltage signals and the current. Sorry, the real time signals are denoted. Then what you do? You sync it with the GPS time using using a sampling theorem, which after which you pass it through a DFT discrete. You do discrete Fourier transform analysis. We'll discuss about it as well. So for discrete Fourier transform analysis, you want the 50 hertz frequency component and the associated phasors. So what does this discrete Fourier transform analysis do? It gives you the phasors, not directly the phasors. You still need to do a bit of mathematical calculation associated with what you're getting out of discrete Fourier transform analysis. But what you get is you get the phasors uh, that are of the one had a message. What is PDC? So PDC are phasor data concentrators. Sorry, I saw it very late. So these are phasor data concentrators. So what they do is, I discussed here, right? I guess you were not here. So they gather data. They are bunch of. So you have PMUs at different displays across different the whole architecture of the power systems. You want to send this data first to some place, right? They are receiving data in real time, but you need to have this data collected at some place, right? So that's where PDCs come. PMUs send these data to the PDCs, which then gather data, reject the bad data, align the data with UTC, and record the data as well. So that's why that's what PDCs are. Yeah. So where was I? Yeah. So you get phasor components associated with your time, these voltage and current signals, and after that you can do symmetrical component analysis to get various different quantities. So we'll discuss more in the coming slide. So I said DFT. Why do we want to do DFT? So first of all, what are discrete Fourier transforms? So a discrete Fourier transform converts your signal from time domain to frequency domain. That's the main use of this algorithm to frequency domain. So when you get this data in frequency domain, what happens is you can then use it to only calculate the associated values with your uh, uh, fundamental frequency component, right? So you have a data. Let's say you have uh, something like this, right? So this is your signal, the signal that you are receiving in real time, right? So this signal has harmonics, right? Because it's distorted from how it looks, how it, yeah. So because it's distorted, so it has harmonics because it does not look like fundamental component associated with the time. So we know what is the fundamental component. So what we know that its maximum for let's say the voltage signal at our house, it's 230 volt RMS, right? And it's the frequency is 50 hertz. So the value of the magnitude and the phase angle associated with fundamental frequency component is what we are looking for. We can do harmonic analysis also, but the phasors are generally calculated only for the fundamental frequency component because that is what is being used at the end. So what you do, you convert it into the frequency domain. After you convert it, you can reject the higher order or the low. It's difficult to calculate the lower order, but let's say for the higher order, you can discard it, and then you can get the fundamental frequency component associated with your signal. So how you can do that? So let's say you have a signal xk. After discrete Fourier transform, this signal you get. So before that, it's something like this: 1 minus n, and from 0 to n minus 1, you have your continuous samples. So you have a signal xt, which is something like this. You are sampling in real time, right? So xn is nothing but your samples. So x1, x2, x3, which are these x1, x2, x3, etc., right? So this xn, and it's coupled with this 2 pi n upon n, right? 2 pi n upon n and k. So this k tells you what component are you interested with. So if k is equal to 1, it's fundamental component. And if it's 2, it's the second harmonic, which is 100 hertz. But you are only concerned with 50 hertz signal, right? So you usually use k is equals to 1. So you must have seen in ma'am's lecture as well. She has uh, this vk, which is denoted as 2 by n summation n equals to 0 to n minus 1 vn e minus j 2 pi n by n. Right. So can anyone tell me why are we scaling it with 2 here? Anyone who has an idea with discrete Fourier transform? Yeah. So with Fourier transform. So it's called discrete because you are taking discretized samples of your time signal, right? So you're sampling it with discrete signals. So that's this xn is discrete. That's why it's called discrete Fourier transform. Yeah. So why are we scaling it with 2 by n? She didn't explain it in her slides, but you must have had this question if you would have if you watched the lecture. I hope that you watched. So can anyone tell me why is this scaling of 2 by n coming into play? No one? Okay. So this scaling generally comes because of this. Let's say you have a signal a cos omega t, right? When you write it in frequency domain, how do you do it? Sorry, exponentially. You know, cos is represented as what? Eij plus e minus ij. Sorry, why am I writing ij? Ei omega plus e minus I omega upon 2, right? So to get this signal, 2 cos omega t, you have, sorry, a, we multiply it with a, right? So you have a by 2 e I omega plus a by 2 e minus iota omega, right? So you get these two signals, right? Now, here, if you check the component that is more relevant to the discrete Fourier transform, it's scaled by uh, 1 by 2 of the whole signal, right? So to get the scaling done correctly and to make sure that your Fourier transform is able to replicate your signal correctly, you need to multiply it with 2 so that this term by 2 doesn't come into play. Otherwise, what happened? Your signal will be half the magnitude of what it was supposed to be. That's something that you don't want to do. That's why you multiply it with 2, right? So I won't remove this. I'll take the next thing. Yeah. So this is why this 2 comes into play. I just wanted to tell you because I thought people would have checked. Yeah. So and so that's why you do DFT. It's for to estimate phasors by using the by using the continuous time signals that you're getting. You discretize it, you sample it using a particular sampling frequency, which is generally which is at least twice the maximum component associated with that signal, frequency component associated with that signal, and then using that you can calculate the voltage angle and the the voltage magnitude and the voltage phase, and through which you can calculate uh, the voltage phasor. So let's talk about what are these different kinds of DFT. So in full cycle DFT, let's say you used 1 kilohertz sampling frequency, right? Yeah. So can anyone tell me for a 50 hertz signal, how many samples will it take? If you have a signal, this is a 50 hertz signal. So So what is the number of samples going to be? Anyone? Okay, so it's Fs upon F naught, which is 1000 upon 50, which comes out to be 20. So the total number of samples for one full cycle will be 20. So when you do for a full cycle, so your Fourier transform would look something like this, right? So you will sum it from 0 till n minus 1. That is, you are taking the whole 20 samples that you used to to sample the whole cycle of that to the one cycle of that signal that you want to capture. In half cycle, what you do is you calculate for a half cycle only. Why? Because generally the system's voltage and currents are functions of cosine and sine, right? And they are what they are symmetric across half cycles. So you can use half cycles as well to calculate the Fourier transform, and it would look something like this. Since you are doing it for half a cycle, one more scaling factor will come. You will have to multiply it with twice because the number of cycle you're calculating only for half cycle, right? Yet you require the DFT for the full cycle, so you have to multiply it with 2. So I'll show it something like this. It would be Vk, which is 2 times 2 by n, summation n equals to 0 to n by 2 minus 1, this term, right? So you use it to calculate for half a cycle. Now, what is cosine DFT? So why we are doing only for half a cycle? It's to increase the time because you need to calculate the sample for the whole cycle and then you will be able to derive the DFT, right? But here, what you can do is you can calculate only for a half a cycle, yet you can get the equivalent uh, component that you wanted with the lesser amount of time, and the computation resources required will also be less. For cosine DFT, the thing is completely different. So one thing I forgot telling. So can anyone tell me this signal in terms of cos and sine? How will it look like? I'll do it. Not something that's measured. So it would be two. Your scaling factor is still the same. You have Vn cos of 2 pi n by n. And here the imaginary one will be associated with the sine one, n by n. Right. Now, if with cosine DFT, what you want to do is you want to calculate only the cosine function, right? So you have cosine function, which is represented by VCN. Uh, yeah, uh, cos 2 pi n by n. Right. Now, can anyone tell me how are cos and sine functions related to each other? Yeah. One more thing. If you have these two real and imaginary part, you can get the magnitude, right? It would be what? V real square plus V imaginary square, and the phase angle will be nothing but tan inverse V imaginary upon V real. So that's how these phases are calculated. So I thought that was pretty evident, but yeah, still not. So can anyone tell me how cosine and sine functions are related to each other? Anyone? Anyone? No. Okay. So can I say that cos leads sine by 90 degree? Is this statement correct? Yeah, phase difference. Yeah, but what I'm saying is, if I say that cos leads sine by 90 degree, is this statement correct?
Yes, sir.
Yeah. So then I can just write it like this, right? Uh, so if you have a signal, let's say something like this. So you have a cos signal like this. Sorry, diagram is pretty poor. Right. So at let's say these two things, the difference is of, so for one full cycle, uh, that is for n, you are doing for 360 degrees, right? For 90-degree difference, what you need is n by 4, right? So if you sample, let's say if you use the sample that was there n by 4 uh, times back, that is, since the cos is leading sign by 90-degree, what you can do is you can use the sample that was there n by 4 time n by 4 blocks away. So that means, let's say you have 20 cycles, 20 samples. So when you are at sixth sample, let's say, you would need to calculate, yeah, you would use the first sample of the cosine function to denote it as the function for sine only. So that's how you can get the DFT without requiring to calculate the whole full cycle function as well. So that's how it comes into play. In recursive, what you do is you use windows. So if you have a function, let's say like this, a signal like this, so you use windows, let's say for 20 samples, you use multiples of these windows to calculate your DFT. So due to which, what happens is you will require to calculate only once, right? For example, in this sample, in the blue one, the light blue one, you have the samples for this region because you already calculated for a window before. Now you need to calculate only for the next 2 or 3 instance, depending on how the window size is. So the computation power used is all the way less. So that's how these DFTs are used. But since you're not doing it for the full cycle, what happens is you may miss 1 or 2 components that could influence your decision. But that generally doesn't happen. All of these offer similar accuracies compared to each other. But mostly we use recursive DFT because of the computational, because it uses lesser computation time and you get the maximum benefit out of your PNB, right? So this is how DFT is used to calculate or estimate phasors. So this was, so if I show it something like this, so you had a signal varying like this. So you use it to, you sample it using a particular sampling frequency. After you get those samples, you do what? You use DFT to calculate its component, both real and imaginary. After you get the real and imaginary part, you can use these uh, properties to get the magnitude and phase angle difference. And you will see that magnitude will remain constant if and only if the voltage is not, the fundamental component of the voltage is not varying by much. And the phase angle, because it's rotating, it will change depending on how the signal is behaving, right? And this is not the only way. You can also use another phasor estimation technique, which is called least square based estimation. So what usually happens is, even though you can find DFT for a higher frequency component by using the K here, this K, right? Yeah. So you can use this K to figure out for different frequencies, but you can go below fundamental frequency. That is, you can't find DFT for subsequent synchronous frequencies, which is also something that you want to do, because it's not like the frequency won't go below 49, won't go below 50. Just a second. Yeah. So that's where least square based phasor estimation comes into play. So what you do, you want to calculate for subsynchronous, you need to do it like this only. But there is one major demerit associated with it: synchronous frequencies. So the demerit is computation. You would require to inverse a matrix, and inversion of matrix, uh, the difficulty of inverting a matrix increases with the number of samples it has, or decreases with the number of size of the matrix, right? So if the size increases, it becomes harder to invert it as well. And sometimes what will happen, the matrix you have is won't be invertible also, so that will also be a case. But still, it's a healthy it's a healthy way of analyzing things. So what you do is, you know the relation. Let's say this is something you are trying to calculate. What you say, you are trying to, you know that the variables vary linearly with, for the measurement. You're measuring something, and you know it varies linearly with time, right? So I can write it something like this, where A and B is something that I'm trying to estimate, while M is the measured value, right? So let's say that I do it for many times. Let's say for T1, for T2, it comes out to be M2, etc., etc. For N times, it comes out to be N, right? And let's say now you are, since you got all of these values, you are able to estimate it as well. So let's say you have estimated these values. So you can write it something like this: A cap plus B cap T2 M2, right? So now, after their estimation, sorry, the measured value and the estimated value will have some error, right? Because it's not like your estimate will always be correct, but it's healthy to calculate the error, so that if the error is not very high, you can always use the estimated values of those parameters to calculate your measurements. So let's say this is how you calculate it uh, uh, for your uh, uh, for your parameter, right? I need one more page. Yeah. So I can denote it using a matrix form. It would be something like this. One, sorry, it won't be a big matrix. It would be two, one cross two, right? One T1, one T2 till one in Tn minus. Oh, sorry, it was in multiplication with A cap and B cap minus M1 to Mn, with your errors being from E1 to En, right? I can always denote my system of equations in a matrix form. So let this matrix be A, and let this be your estimated AX. This is M, and this is E. So you can denote your matrix by something like this: A X cap minus M equals E, right? So now, what I want you to do is, um, uh, multiply the transpose of both of these metrics at both sides. Transpose, right? So it would be something like this: E transpose E, which would be something like A X, sorry, right? So once you get it, now you would be wondering why it's called least squares, right? So once you get this transpose, and if you know if I have something like this, right? 1, 2, 3, and its transpose is 1, 2, 3. If I multiply it, what will it be? 1 square plus 2 square plus 3 square, right? It would be a 1 cross 1 value. It would be a single value where it would be the summation of all the squares of the individual values, right? So similar thing, similar approach, we get it. We multiply it with transpose with both sides, and what we have is we have an error square. This is generally denoted as this form, which is called L2 norm, and this is the rest of the parameter. So what you want to do is you want to least square them, right? So you differentiate both sides and equate to 0. Now I want, so if you want me to do if you want me to calculate the whole thing, let me know right now so that I'll calculate everything. But if you want to try it on your own and you just want the final values that are given in the PPT also, but I am going to tell you this: the final thing seems to be incorrect. So uh, if you want me to calculate it right now, I can do it. But if you want to do it on your own, feel free to do it. But the thing that I want you to know is that the final value over there is incorrect. That's not how the pseudo inverse is supposed to look like. I guess they missed an inverse in between. That's what my because I calculated everything and I'm not getting the same exact expression as they have written on the PPT. So tell me right now if you want me to do the whole calculation. That's why I'm going to do it because it's incorrect over there. So, do you want me to do it?
Sir, just give us the final value so that we can match after deriving.
Okay, okay, okay. So, if you differentiate both sides with respect to the estimated value, you'll get it something like this. The x cap would be A transpose A inverse A transpose n. This is how the final expression would be. If there won't be a an inverse of this thing, there is an inverse of this thing as well. It won't be there, and this is called as pseudo inverse, right? So I want you to do it once so that you feel comfortable on how the whole thing looks. But yeah, so so this is how the final expression will look like. So this is one way in which you can estimate parameters by using least square method, and you can do this by estimating how the phasor estimates would look like based on the measurements, and then you can get the phasor values using the pseudo inverse phenomena. So this is how phasor estimation is done. It's done using two things: DFT and least square based methods. But since subsynchronous frequency is something which is not dealt with properly in DFT, we use least square based methods as well. One more thing, it's fairly easy to do it in MATLAB as well. So you can just use pseudo inverse in MATLAB to calculate the pseudo inverse as well. So you can get this done over there as well. So is everyone on the same page as of now? So a yes or a no. If you want me to repeat something, please feel free to say. It's not something that I can't do. A thumbs up or a thumbs down. So is everyone on the same page? Is everyone getting everything? Okay. So you can always rewatch the lecture and comment on the YouTube comment section as well. I'll be happy to help you. Next thing, so you got the phasor estimates, right? Now you want to estimate frequency as well, the frequency as well, because what you are doing right now is in DFT, you can calculate it at different frequencies, but you won't be able to get the how the frequency is varying in real time. Like, for example, 49.95 to 50.1 is the band that we want the frequency to stay in, right? So to monitor that, you need to do frequency estimation as well. So there are two ways in which you can do it. One is zero crossing based method, in which you take a signal, then check how long the zero crossing takes time. So if you see the signal here, it starts increasing. So slope of this this the slope of this curve is increased, is positive, right? So you take the time at which it happens, and then you see if the next time the same frequency, the same slope is coming into play. You get the two time instance. Now you know the two time instance. You can easily get the total. So this would be your T naught, and the F naught will be 1 upon T naught, right? So by checking how the zero crossing is occurring in your system, you can get the frequency of the signal also. Also, you can use phasers. So phasers are rotating, right? When they rotate, their phase angle increases and decreases in real time. So you can check the rotation of the phase angle, which would be something like the Fs would be 1 upon 2 pi delta omega by delta t. Sorry, I wrote it wrong. It would be, sorry, the frequency would be 1 upon 2t 2 pi delta omega, right? Oh, sorry, delta phi by delta t. On how the phasors are changing, the phase angle is changing, you can calculate the associated uh, uh, the frequency as well. So there are two ways which you can measure the frequency. So you got two things. So two major components is your phasor, your voltage, magnitude, and angle should be known to you so that you can estimate the state of your system correctly. Second, your frequency component also must be known to you so that you can check whether the system is behaving perfectly and your frequency is within the band. So these are the two ways in which you can measure the frequency. Now, after you know the state of the system, you also know the frequency. What if things go south? So let's say your state of the system tells that your system is transcending towards an anomaly, or it's going towards a system which is difficult to operate. So for that you need protection. So that's where these protection equipments come into play. So I already told you when there was central generation. Yeah, when there was central generation, the power flew only from the generation to the distribution side. Now, with the onset of PV, batteries, fuel cells, gensets, etc., the distribution system has become more active. So, since the distribution system has become more active, you are continuously witnessing areas of brownouts or blackouts because of things not going to how you wanted them to go, right? So what used to happen before, you had different protection devices. What were these protection devices? These were switches which were operated by relays, and you had reclosers, etc. So your relays in real time tell if you want to open a switch or not, if you want to trigger a fuse, like let's say a fuse or not. So these relays control your switches so that you can easily distinguish fault, and then you can disconnect the faulty line so that the fault doesn't travel to the extreme end. So before, what used to happen, you used to have electromechanical relays. So these electromechanical relays had moving parts, and with the evolution of time, you went to static relays. So these static relays did not have any moving parts. They were just they just used to send signal in analog form to your switches. But you used to have AD converters at both ends because you need to convert your analog signal to digital to be able to travel that whole path, right? Your switches won't react to your uh, analog signals. They will only react to binary inputs, right? Zero or one. They need just two signals. So then you thought, let's go with digital relays, right? With evolution of time, that's how you want your system to progress, right? You got processors, processors became cheap. Now processors were available in different forms at different sizes, and you knew that the the scale of the relays will now decrease as well. So that's why you progress towards digital relays. Huh. And the advantages were nothing but your cost. So I won't say digital relays are extremely inexpensive. They are expensive, but the overall cost of maintenance, operation, etc., reduces their total cost that you experience in real in the entire life. Second, they were self-checking. So what do I mean by self-checking? They can sense the fault and they can issue commands based on how the fault is happening. So they were reliable as well. So we will discuss what is reliability and stuff. They were auto reclosing, etc. So you can check all of this in the slides as well. But when there are advantages, there are disadvantages as well. So the disadvantages are few. So one, they are prone or susceptible to electromagnetic interference or radio frequency interference. So these are two interferences that affect the how the digital relays will work. Second, if at all a fault is able to what to say, if a fault is able to uh, go beyond a certain operating limit, their life is very short because they won't be able to maintain. They won't be able to what to say experience that fault for a very long time, and they will uh, shut down. Right. So this is how a subsystem of digital relay look like. You get current and voltages. You remove any surges they may have. You condition the signal. You sample it correctly. You get it out of you get it out of how the thing would look like, only the fundamental frequency component. Then you used to send it to the AD converter, where where you send it to the processor, where the commands are issued using the digital output connection. So this is how a digital relay looks like from inside, right? And they have three main memories: one RAM, one ROM, and one EPROM. Which is RAM is random access memory, read-only memory, and erasable programmable read-only memory, right? So these all of these have different functions. RAM is used to store data for a particular time instant only, while ROM is used for data storage for a longer time. And EPROM is where you issue commands. Is holds the program where commands will be issued for your system. And you can't just connect it to your CT, right? So you have a particular standard. So Indian standards say for relay, the current must be either 1 ampere or 5 ampere, and the voltage is 110 volts face to face. So this is the standard. So relays operate only in these particular currents and voltages. And how do you ensure that? It's by either you can connect it directly across your main CT, your primary is connected across your transmission line, and then you can use the secondary to send it to the various relays and meters, or you can connect an auxiliary CT where you can tone it down even further and then send it to the computer relay. Or for voltage, what you do is you use a voltage transformer where you divide the voltage so that to get it accurate, so to have what you say a safe voltage to be given to the relay. Here also, I told that you need to sample it accordingly. This is similar lines on how I explained previously. If you sample it correctly, you'll get the exact replica of your signal. Otherwise, your signal will become distorted, which won't have the perfect effect that you want to have on your system, right? So So now the relays have three major differentiators. It's the reliability, dependability, and security. What is reliability? So you want your relay to work at all times, right? So it shouldn't be like your relay, what you say, let's say a fault occurs and your relay gets damaged, but you still want that fault to be curbed, right? So how you can ensure that that fault doesn't harm how the relay is supposed to work? You can have a backup relay connected to it, right? But that backup relay, if you are connecting, you're increasing the cost of the system, right? But but that's something that you have to check. So redundancy, which is that you increase the number of relays connected to that system to be able to shun the fault altogether. So to measure reliability, what you do is you calculate the number of correct trips that it does, divided by the total number of desired trips that you wanted it to do, plus the number of incorrect trips. So the relay could incorrectly as well trip a line, which is not supposed to do, right? So that's something that your relay should not do. So this is the reliability index. That's how you calculate the reliability index. Dependability is when you want it to trip when it is expected to. Let's say a fault occurs, you want it to trip, but it doesn't. So it's not dependable, right? So to measure it, the dependability index is given by number of correct trips upon number of desired trips. And third thing you want is security. It should not false trip in any location which it is not supposed to do, right? So how do you do it? It's number of correct trips upon number of total trips. So we will discuss more about it in the coming week, where we will go through various protection schemes and how protection is done for the whole smart grid environment. Right. Yeah. So that was all for today. So today we discussed what is wide area monitoring system, why we require wide area monitoring system, how states need to be checked at all time for the system. How can states be checked? It's through phasor estimations. These phasor estimations can be done either through DFT or least square based estimation. Then once you get the state of the system, you also want the frequency to be within the safe limits. For that, you do frequency estimation. Frequency estimation is also of two types: zero crossing and this phasor rotation. And then we talked about protection, because you got the state of the system, you knew frequency of the system, but let's say any anomaly happens or any abnormality happens, how your system braves through that anomaly is how your smart grid protection should behave, right? Also, we discussed what are PMUs. This was a recap of what we discussed in the first lecture, and I just discussed all about it. So any doubts before we move on to the questions? Anyone? Any thumbs up, any thumbs down? So did everyone get the lecture today? I know it was very heavy on information, but the whole week was very, they covered a lot of information this week. So I hope I was able to simmer it down. Yeah, I would like you to check if you are able to get the same thing, right? If you don't get it, please let me know in the comment section and I will send you a link for the whole derivation as well, which I did. Okay, so shall we move on to the questions? Any response, please? Yes. Okay, so first question, it's a database question. It's taken from the uh, uh, first lecture of this week. So can anyone tell me if anyone followed the lecture of this week? I didn't cover it today. So what is the sample rate of digital fault recorder? So since it's something that I didn't cover, it's 64 to 356 samples per cycle. So the digital fault recorder, which measures how many, so to be able to get how many, so to record faults, what you need to do is you need to have transient observability of the entire system, right? In order to have transient or dynamic observability of the entire system, you need to have more samples per second per cycle of your system. So that's where this comes into play. Okay, the circuit breaker monitor data is also formed in what format? Okay, this is so the format they are asking, it's Comtrade format. Yeah, so this is something that I covered today. So which of the following phasor estimation technique can filter exponential DC components inherently? So can anyone tell me? So we
Least
covered,
square.
yeah, it's least square estimation technique because if let's say you have an exponential DC component, it's a component that is going to 0 hertz exponentially. So you can only cover it because it's a subsynchronous frequency. You can only filter it using least square estimation technique. Now in GPS, each satellite covers what percentage of the globe? This also I covered.
42%.
Yeah, it's 42%. Correct. In WAM's technology, non-operational data is used in. So in the beginning of this week, the instructor covered two forms of data that WAMs used. It's operational as well as non-operational. I didn't cover it today. So, so can anyone tell me?
Digital fault recorder.
Um, I think it's all of the above.
Okay.
Sir, all of the above.
Yeah, it's all of the above, right? Okay, so if a signal has a fundamental frequency of 100 hertz and it is sampled at a sampling frequency of 30,000 hertz, then the number of samples per cycle is? Who will tell me?
300.
Yeah, 300. Okay, so someone is very fast today. Okay, so 300 cycles. How do you calculate it? It's simply Fs upon F naught, which is 30,000 divided by 100, which comes out to be 300. Now this question, a 100 hertz voltage signal is sampled at 5,000 hertz, then the phase angle between the two successive phasor estimated by DFT is? Who can tell me now? So you have a signal. So your signal is a 100 hertz signal and you are sampling it at 5 times the frequency, right? So let's say, okay,
7.2 degree.
okay, 7.2 degrees is the correct option. But to have everyone on the same page, let me tell you how it comes. So when you're sampling it at different samples, so each of your phasors that are estimated, this sample, sorry, yeah. So this is your omega t, right? So this is degrees only. Let's say you had a signal xt. So you want to in order to know what is the what they say the phasor difference between these two samples, that is the phase angle difference, that is the theta between these two angles, is nothing but 360-degree into yeah, f naught by fs, right? Yeah, so it's 360-degree into f naught by fs. So if let's say your signal has a fundamental frequency component of 100 hertz and the other is 50,000 hertz, 50,000 or 5,000, right? So this comes out to be 7.2 degrees. Let's say your signal was of 50 hertz f naught and your sample frequency is 1000 hertz. What will be the theta now? Can anyone tell me quickly using this formula?
90 degree. 90 degree.
No, 90. It won't be 90, na? It would be 18 degrees, na? So you
18.
use the
Yeah.
formula, yeah, 360-degree into 50 divided by 1000, which will be 1 by 20 multiple 360, which is 18. Okay, so the relay percentage of security is defined as, I just told, uh, just told. So I would want someone to answer it. I won't go back to that page, that slide.
Second one, sir.
Someone said second one. No, no, it's not the second one. Oh, someone said three. Okay, so it's number of correct trips upon total number of trips, right? So you want to tell how many times. So you want it. So what is security? You don't want it to falsely trip at a point which you don't want it to trip. So that's that number you can get it from number of correct trips divided by the total number of trips that it has done. Okay, what is the advantage of digital relays? It's very easy, right?
All of the above,
All
sir.
of the above.
Yeah. Okay, last one. In the signal, no, it's not the last one. Yeah. In the signal, first zero crossing occurred at 0.01 and the ninth zero crossing occurred at 0.05. Then the frequency of the signal is. Can anyone tell me? Sorry. Let me know if you're doing it. Otherwise,
Sir, 50 Hz, sir.
you someone said 50 hertz. No.
Why, sir?
So remember, it's saying first zero crossing. So it's not showing at. So when I told you about zero crossing, I was mentioning one thing: the slope must be positive. It's just showing first zero crossing. That means it's calculating for the slope that was positive as well as negative. So if you want to find it for the whole cycle, what you do is you only do it when the slope of the signal was positive. Like say for this, so you get the whole cycle. But right now it's telling for it did not tell what is the zero crossing that it's talking about. It's just simply referring it to as first zero crossing. So can you now tell me what will be the answer? Yeah. So this was 0.01. This was 0.05. In between them, there was 0.04 difference in total of 8 zero crossings. So that means each crossing happened at which interval? Can anyone quickly solve this and tell me? It was 0.005, right? So that means this was 0.015 and this was 0.02. So that means the time of the time of one cycle is 0.01 second. So that means the frequency is what? 1 upon 0.01, which is 100 hertz. So the answer is A. Yeah, don't confuse yourself with the terminology. So when it says first zero crossing, it means the zero crossing only. So the zero crossing is happening here as well as here. That is something that you didn't take into account. If I would have written here that the first zero crossing with positive slope occurred at 0.01 and ninth zero crossing at positive occurred at 0.05, that's where the frequency would have been 50 hertz. Okay, next question. So you understood, right? Who was the one that answered it? I want him to. Who was the one who just answered 50 hertz? Uh, I mean, yeah. Who?
Nitish Kumar, sir.
Yeah. So you got it, na? What I'm telling or what the correct way of answering that question is?
Yes, sir, I understand, sir.
Yeah. Any doubt? Please let me know. So it's talking about first zero crossing, not the first zero crossing where the slope was positive.
Okay, sir.
Yeah.
Thank you, sir.
Hmm. Next question. Which of the following is not true about SCADA? Can anyone tell me the correct answer?
A.
Yeah. So it does not. It does not measure the phase angle. It only measures the magnitude. So this is not a true fact about SCADA. Second question: what do synchronized phasor measuring units systems measure?
All of the above.
Yes, it's all of the above. They measure voltage magnitude as well as phase angle, current magnitude as well as phase angle. Which component of synchronized phasor measuring systems creates a record of recorded data?
PDC.
Yes, it's PDC. The phasor data concentrator is responsible for gathering data, recording it, and then removing bad data as well. Fourth, which of the following is designed to isolate the area of faults and reduce the impact of faults from other parts of the system?
CBM. Circuit breaker recloser. I think so. Recloser, yeah.
Uh, hmm. So I don't remember the exact definition of CBR, but circuit breaker monitoring is the one that is designed to isolate the area of fault. It should be CBM. Who mentioned third? Shibna. Okay, it's CBM. It's not CBR. It's recorder, I guess. Circuit breaker recorder or data recorder. It's not something that monitors it and isolates it. It's the CBM that does it. Okay, so a central PDC is installed at NLDC. Where is NLDC located? So
Please, sir.
now the
Delhi.
yeah, it's Delhi. Now it's not called NLDC anymore. It was called POSOCO, and then they changed their name to what is it now? Can anyone tell me?
5, sir.
Uh, what are they called now? Anyone who knows what is the National Load Dispatch Center called now? They recently changed their name last year.
Grid
I remember.
controller.
Yeah, it's Grid Controller of India. Yeah, GCIL or Grid India as well. They have a shorter form as well, Grid India. Okay, according to the sampling theorem, the sampling frequency must be greater than dash the highest frequency to be sampled. Can anyone tell me?
2 times. 2 times.
Yeah, it's 2 times. Eighth, the recursive DFT dash the number of mathematical operations.
Reduces. sir.
Reduces.
Yes, it reduces the number of mathematical operations that are required. Yeah, phasor estimation based on least square error method can be applied for signals with decaying dash component.
DC component.
Yes, DC component. Last, what are the disadvantages of the traditional relays?
All of the.
Yes, so their production facilities are now aging. They also have discontinued manufacturing of some components and parts. Also, there is a shortage of their testing technicians. That's what has led to the evolution of relays to digital relays. Yeah, so that's all that we wanted to cover today. So we still have some time left. Uh, so we covered a lot of things today. I skimmed most of them. So it's WAMS, which is wide area monitoring system. We covered why wide area monitoring system is required. How is it different to SCADA? Then we talked about PMU. What are PMUs? What are their benefits? What are their applications? Then we talked about how SCADA and PMUs, what are the differences between SCADA and PMU. Then we talked about PMUs, how the data is concentrated and where is it sent. Then I gave you this example. Do make sure to check out if you are interested to know how optimization of these how optimal PMU placement of these PMUs is done. Then we talked about its applications, WAMs. Then we talked about smart grid monitoring, how the PMUs are linked to the GPS clock, the block diagram, how sampling affects the signal, and what is aliasing, how to remove them. It's simple. Just sample it through a frequency greater than 2 FM, or use a the RC filters. So how distribution system state estimation is done? What are states? These are two things: magnitude and phase angle of the voltage. And then how the the PMU operation is done, what are the various components required. Then we talked about how phasors are estimated using DFT, which had full cycle, half cycle, cosine, and recursive. Then we talked about least square based estimation. Please make sure that you do this derivation. It's very easy. I've given you this. Just expand it and differentiate with respect to x. And then how to estimate frequency, why to estimate frequency, then protection, and then digital details. Any questions from this class before we close? Anyone? So did all of you understand today's class? I mean, I need honest feedback from you all. If I covered it at a pace that was not something that you could have, so I would like to give you my sincere apologies. Okay, thank you. Okay, so let's close today's meeting if there are no further questions. So thank you all for joining. We'll meet again next Saturday, 6 p.m. Yeah, thank
Thank you,
you.
sir.
Bye bye.
Bye, sir.
Bye.
Thank you, sir.